Okay, hello. So welcome to the third edition of the AstroCheminar. This is the online seminar series of the American Chemical Society's Astrochemistry subdivision. I thank you all for joining us this Veterans Day as we salute our men and women in uniform who fought for our country and still continues to fight for our freedom. I'm Prof. I'm joined by Heather Abbott-Leon, Ryan Fortenberry, Kyle Crabtree, and David Woon, and we will be hosting this meeting. The AstroCheminars are free and open to all, and they're recorded and later uploaded to YouTube. Please subscribe to our YouTube channel to see these videos later, and also help us get a good URL. Our next seminar will be on the 9th of December, so please also join for that. And please contribute talks in this seminar series by sending us an email or filling up the form in the website. In today's AstroCheminar, we will first hear from Beatrice Kulterer about astrochemical modeling, and later from Professor Susanna Widicus-Weaver. The first talk will be given by Beatrice Kulterer. Beatrice did her BSc in Earth Sciences and MSc in Astrophysics from the University of Vienna in Austria. Then she started her PhD in astrochemistry at the Center for Space and Habitability at the University of Bern in March of 2009. Beatrice is a PhD student with Dr. Maria Drozdowskaya. And she'll be talking about astrochemical modeling today. So go ahead, Beatrice, share your screen now. Oh, just a quick reminder before I let Beatrice start. Beatrice, go ahead, share your screen. Please keep your voice and video off for the duration of the talk. And if you have questions, please put the question down in the chat box, and I will, or Heather will read it out to the speaker at the end of the talk. Go ahead, Beatrice.
Okay, thank you for the introduction, Partner. Welcome. My name is Beatrice Kulterer, and I'm from the University of Bern, and a second-year PhD student. I'm very happy to share the first project of my PhD with you, which is titled Physical-Chemical Models, Source Tailored or Generic, and where I try to assess based on the analysis of simple molecular species and free physical-chemical models if these always need to be source-tailored, or if we can also learn from generic models, if they can better our understanding of low-mass star formation. So just to make sure that we are all on the same page when I'm talking about low-mass star formation, small recap what I mean. So low-mass star formation starts in dark cloud cores, which are cold in temperature with around 10 Kelvin and gas densities in the range of 10 to the 4 to 10 to the 5. Most of the molecules are confined to the solid phase. Once the density exceeds a critical value, star formation starts. So you start to form your protostar at the center of the core, and you have infalling material from an envelope and a forming disk. And after a couple of 10,000 to 100,000 years, your protostar will be born, and it is still deeply embedded in an envelope and the disk. There might be outflows or jets. And then later stages, the envelope will have dissipated, but you still have your protoplanetary disk, and this is way before the start of planet formation. And considered in this work are just the early stages, so more or less panel A to C. And what I will be talking about are the physical structures that were obtained with free models, and also at the chemical evolution of these models. And then to assess the impact of the physical models, I redid the chemical evolution of the models with the same chemical network. And I will briefly introduce the free models, but if you want to know more about them in detail, please have a look at the publications that I list here. So the first model is dubbed W14M20 this work, because the physical model is taken from Wakelam et al. In 2014 and was last published in Maligand et al. In 2020. And it is a 1D physical model that traces the evolution from a pre-stellar core to a protostellar object. And it is based on Aikava et al. In 2008. And the density structure used here is derived from single dish observations towards the proto-binary source RS162932422. And this 1D model is coupled to a three-phase chemical network called Nautilus. So you have the gas phase is one, and then your solid phase, your ice, is split into two phases, namely the surface and bulk. And very similar, the second model called S20, which is to be published in Stefan et al. In 2020. It is also tailored towards RS 16293242. And it is also a 1D physical model that, again, features the evolution from a prestellar core to a protostellar object and uses a three-phase chemical network. But in this case, it's magical, as detailed in Garot et al. 2013. And last but not least is a model called D16, which was last published in Rostovskaya et al. In 2016. And contrary to the other two models, this features a 2D physical structure, and it traces an axisymmetric semi-analytic collapse and includes the formation of the disk and traces the history of the system during disk formation stages. And contrary also to the other two models, it only considers a two-phase chemical network, so you have your ice as one phase and the gas as the other. And all of the models are tailored towards low mass star formation and the formation of complex organic molecules. And the calculations are done similarly for all three models. So for the physics, you first run your collapse model. So you look at the velocity and density distributions at each time step for the duration of your collapse. And then you also calculate the dust temperature and your UV field. And this gives you the opportunity to trace the changes along streamlines or trajectories of infalling material. And also all three models do consider the evolution of the protostar after it has been born. And what you basically do is you use your the results from your physical model as an input for the chemistry, which has been calculated in two steps. So first, you have a set of initial atomic abundances, and you evolve these under prestellar conditions for the duration of a pre-collapse phase. And important for this step are the dust temperature and the gas density, as well as the visual extinction and the cosmic ionization rate, which is depicted on the right here. This allows you to obtain your pre-collapse molecular abundances. And I want to draw your attention to the duration of the pre-collapse here. So for the two 1D models, it is 1 million years, and for the 2D model, it's only 300,000 years, and this will become important later. And then the output from this, because now you have your initial molecular budget at the start of the collapse, and combined with the results of the physical model, you can now trace the evolution of the chemistry during your collapse phase. And while the collapse time is similar for all three models, between 250 and 340,000 years, the birth of the protostar occurs at very different times during the collapse. So for the two 1D models, it happens towards the end or at the very end of the simulations. But for the D16 model, you already form your protostar after the first 20,000 years. So this will affect the physical structure of the system. And I will also briefly talk about the physical results from the models. So what is depicted here is one representative streamline per model. So for the remainder of the talk, all output from W14 M20 will be plotted in blue, for S20 in red, and for D16 in green. And what is shown here is on the left the evolution of the gas density, and on the right of the dust temperature as a function of radial distance to the protostar. And these three streamlines have been chosen because they all end up at similar distances, namely between 45 and 60 LU. And what can be seen here is that the 1D models trace the cold dense envelope for the majority of the infall pathway, but then the infall ends in a warm dense environment. So you have dust temperatures way above 100 Kelvin, and the gas density is in the order of 10 to the 9. On the other hand, the 2D model includes a protoplanetary disk as depicted here, because the colored panels here are derived from the generic 2D model, because the 1D model, of course, doesn't feature a disk structure, but the 2D model does. So these are the parameter ranges depicted here. And the 2D model enters the forming protoplanetary disk, where it has its maximum dust temperature actually, and then it travels towards the more dense and also cold midplane. So please keep in mind that the physical structures of the trace systems are different. And now in terms of the chemical evolution, I want to shortly talk about the initial atomic abundances, because they are what you start with, because you evolve them for your static pre-collapse phase. And most important for this work are hydrogen, both atomic and molecular, and then carbon, oxygen, nitrogen, and sulfur. And two things to note from this plot here. For W14M20, all of the hydrogen is initially already in its molecular form, which could be a potential issue because you need atomic hydrogen for hydrogenation reactions on grain surfaces, which should be very important in cold prestellar conditions. And the second thing to notice here is the abundance of sulfur, which is a lot higher for the W14M20 model. And then you take your initial atomic abundances, you evolve them for your static pre-collapse phase. And what is shown on the right here are the 9 molecules that are chosen for this comparison work, namely formaldehyde, molecular nitrogen, hydrogen sulfide, methanol, ammonia, methane, carbon dioxide, carbon monoxide, and water. And I will always show the sum of the abundances, so gas and ice. So what I want to show to you today is I want to highlight the chemical evolution rather than just the partition between the gaseous and the solid phase. And basically what you can see here, all 3 models agree pretty well for molecular nitrogen, CO, and water. And the biggest differences are seen for hydrogen sulfide, which isn't surprising because the initial sulfur budget is different for the models. And also the CO2 abundance for the S20 model is a lot lower compared to the other ones, which could probably be because this model produces more methane and more water, so your oxygen and your carbon might also already be taken up. And species that form via hydrogen addition are a lot less abundant for the D16 model, which has the shortest pre-collapse duration, so timescales are already important before your collapse even starts. And what happens if you look at the chemical evolution during the collapse? So here the abundances of all the 9 molecules are plotted over the collapse duration. And yeah, just a quick reminder, the red and blue lines are the 1D models, which trace the chemistry in the cold dense envelope for the majority of the collapse, and they just enter the warm region close to the protostar at the very end. And the green line traces the inflow from envelope to disk in the 2D model, and the disk entry here is marked by the dashed black line. And the results can be split into 3 groups. So first, similarities are found for the 1D models for all species, and also good agreement for H2O and N2, also for the 2D model. So no big differences found here. Then the second group are CO2 and H2S, because they were already different before the onset of the collapse. So basically, they if you have differences that prevail from the pre-collapse phase, that doesn't change throughout the collapse. And the third group is the group of molecules that are affected by the disk entry, as it would be expected if the material encounters a drastically changing physical environment. So what happens if you include a disk? So if you watch the green lines for these molecules, in the case of CO2, you actually start to produce more CO2 compared to before the start of the collapse. But in the case of the other molecules, we observe depletion here, which is smaller in the case of water, and also the extent is a lot less for methanol and formaldehyde, which could be because they have higher sublimation temperatures, for instance. And towards the end of the collapse, most of them start to rebuild their abundances, but it is very clear that the final abundances at the end of the collapse are dominated by the choice of physical model here. And again, I want to highlight this here again, where the dark green bar shows the final abundance in the mid-plane of the D16 model, and also the final abundances of the 1D models in red and blue. So, and due to the very different physical environments, you can't really compare these abundances, right? So what I then did is I looked at the maximum dust temperature of all 3 models, which is again at the end of the collapse for the 1D models, but just shortly before the streamline enters the disk for the 2D D16 model, which is depicted in light green here. So we can compare the chemistry, speaking in terms of a warm envelope here. And again, still the agreement for molecular nitrogen and water doesn't change. And also the differences for hydrogen sulfide and CO2 persist due to the difference in the initial molecular budget. But for the other species, the agreement is a lot better. So CO hasn't depleted yet for the envelope in D16. And the species that are formed in hydrogenation processes, their abundances agree a bit better, but they are still less, which is again, a matter of time scale here. So this really stresses that the age of the envelope is a factor that needs to be considered when doing modeling work. And finally, what I wanted to do was to highlight the impact of the physical model onto the chemical evolution. So I took the output of all 3 physical models and then recalculated the chemical evolution, but with the same chemical network. And for this, we used the 2-phase D16 model again. And what you can see here is once more the chemical evolution of the collapse. And the solid lines are now the newly obtained results with the 2-phase chemical network. And the dashed lines are just plotted here as a reminder from the 3-phase models before. So we used the initial molecular budget of the D16 model as well as its chemical network and looked at the chemical evolution, and the results can be split into 2 groups mainly. So first, for these molecules, you have the variations that are shown here are just now because your initial molecular budget is different. So this means that neither the different binding energies that are employed by the models nor the different number of species or reactants that you have influenced these molecules at the cold core conditions before and also after the birth of the protostar. So it doesn't matter if you are in a less dense and cold environment or in a warmer and more dense environment. The chemical network shouldn't influence this that much. But we see variations due to the choice of chemical network for instance, formaldehyde and methanol, and also CO in the case of W14M20. But for instance, if you look at the bottom left at the methanol abundance of the red model, so the S20 model, the numbers are not too different. So this seems to show that the 2-phase approach doesn't lead to the differences, but it might be just due to differences from the adapted activation barriers and individual reactions. So this already brings me to my take-home messages here. And yeah, well, so the small differences in physical parameters of the pre-collapse can lead to significant deviations if they are evolved over the typical lifetime of these cores. And the pre-collapse duration also does impact the initial molecular budget at the beginning. So it will also influence your chemical evolution of the model start forming system. But it seems that the results, at least for these molecules here, aren't significantly impacted if whether you use a more sophisticated 2-phase approach for the grain surface chemistry or not. And simplified physical models can be suitable for a first estimate, but high spatial resolution observations that we, for instance, can do with ARMA for the inner regions of those low mass dry forming systems need to be coupled to a more sophisticated model. So that's it for me. And I want to thank again the organizers for giving me the opportunities, and I'm happy to answer your questions.
All right. Thank you, Beatrice, for this nice talk. Is there any questions? So I don't see any question at the moment.
Can I ask a question?
Yes, please go ahead.
I didn't quite get how you did the physical collapse. What type of, it wasn't hydrodynamics, what type of collapse was it?
For the 1D models, it's a free fall collapse.
Okay. Mm-hmm.
So a dynamic, and for the 2D model, it's a shoe collapse. So this is actually a hydrodynamic simulation.
Sorry, was that the end of the answer?
Yes.
Okay, okay, all right. Go ahead, somebody had something to say? Okay, well, I don't see any more questions. Thank you, Beatrice, for this nice talk. I'm going to go ahead and get started on the next talk. So thank you again. Our next talk is going to be given by Professor Susanna Widicus-Weaver. Susanna Widicus-Weaver is a Vodza Professor of Chemistry and Astronomy at the University of Wisconsin-Madison. She received her BS in chemistry from Wesleyan University and received her PhD in chemistry with Professor Jeffrey Blake from Caltech in 2005. And she was the Green Bank Observatory Fellow during her graduate studies. She then did her postdoctoral fellowship at the University of Illinois with a joint appointment with Professor Ben McCall and the Karma Observatory. She then began her independent career at the Emory University in 2008, where she received tenure in 2014. And then she was promoted to the full professorship in 2019. Susanna recently moved to University of Wisconsin-Madison, and she also served as the ACA Subdivision Astrochemistry Officer, completing her term as a chair in 2018. Her research focuses on the formation and evolution of prebiotic molecules as stars and planets form. Her research group conducts a combination of laboratory spectroscopy, observational astronomy, and astrochemical modeling. So without further ado, here's Susanna Widicus-Weaver. Please, I can see you shared, so go ahead, please.
Thank you, Partha, and thank you to all the officers for inviting me to give this talk. I apologize in advance. Today of all days, my neighbors are getting a new roof installed, so if there's hammering in the background, I'm sorry. I want to talk to you today about the research that we've been doing recently in my group. As Partha said, we moved from Emory University to the University of Wisconsin-Madison. I moved in May, the group moved over the summer, and we're just getting back up and running, but we have some really exciting new results from one of our projects, and I want to tell you a bit about that today. The topic that I'll talk about today, the graduate students that have led this effort are Haley Bunn and Chase Schultz, and then Chris Jernigan from Tim Bertram's group at Madison is in the lab right down the hall from us, and he's been helping us with some kinetics modeling of some of our experimental results. So if we take a look at astrochemistry, I feel like this may or may not be appropriate for this audience, but if we have any students in the audience that are interested in astrochemistry and wanting to learn more about it, astrochemists do a combination of laboratory, observational, and modeling work to try to understand the chemistry of environments in space. The laboratory work is focused, well, at least to some degree on spectroscopy, but also kinetics measurements and other measurements that will tell us things about the reactions that are important in the interstellar medium and the molecules that we're interested in the interstellar medium. The observations motivate a lot of the work in the lab and the models because they tell us the molecules that are out there and their abundances and temperatures, their spatial distributions, and the kinematics of the sources. And so we can put that together then and try to understand how the physics affects the chemistry and vice versa in these objects. And then the modeling ties all of that together, as we just saw in the last talk, which was quite beautiful. We can choose a set of chemical reactions and a set of physical parameters, and we can try to model these sources and understand what we're seeing from the observations and match that with information that we can gain from laboratory studies. My group does a little bit of all three of these things. I'll focus today primarily on laboratory work, but I will touch on observations and modeling. So the key research questions in my group are: how far can the chemistry go in space? When you go from an interstellar cloud to a star forming region, to a planet forming region, to a solar system, where along that pathway does chemistry that's relevant for biology emerge? And how do the different physical environments in each of those regions affect the chemistry that we observe? So if you take a molecule like glycine, can you make glycine in an interstellar cloud? Or do you need a comet or a meteorite or even an Earth-like planet before you can make something fundamental to life like glycine? My work is motivated by comparison to observations, and I wanted to start with these spectra because this really motivates the project that I'll be presenting today. These are astronomical spectral line surveys of 32 different regions of space, all known to have high abundances of organic molecules. The two that everyone starts with if you're looking for molecules in space are Orion and Sagittarius B2. These are the top two spectra here. I've scaled everything up to even get them on the same scale intensity-wise as Sagittarius and Orion. But if we take a look across all of these other 30 sources, you can see there are a lot of overlaps and spectral signatures between these sources. This is the CO line at 230.5 gigahertz. We have methanol branches, we have methyl cyanide, ethyl cyanide. There are a whole suite of organic molecules that we see in these sources. And what we were attempting to do by taking all these spectral line surveys was to try to pull apart what trends we might be seeing in the data. If we look at source age, if we look at physical conditions like temperature, density, the type of environment around it, are there shocks, are there stellar outflows, all of these things, how does that affect the chemistry? And do we see any trends in this data set? We can assign a lot of the lines in these data sets, but there are still a lot of lines from different molecules that haven't yet been studied in the lab that need to be identified. And that's really what motivates my group and the research that we do in my lab. So if we take a look at the chemistry that is understood in the interstellar medium, we know that in warm regions of star formation, it's all gas phase chemistry. All the molecules are in the gas phase. And we know that ions have to drive that chemistry because the attraction between an ion and a molecule with a dipole moment is actually what leads to the enhanced chemical reaction rates that lead to the chemistry that we see in space. But in these colder regions where things aren't in the gas phase, we can still see chemistry in ices. And we can also start to see chemistry evolve as a source goes through the warm-up phase as a star starts to form. So about 15 years ago, I worked with Eric Herbst and Rob Garrett to develop a chemical model trying to explain the abundances and even the presence of some of the organic molecules that were commonly seen in star-forming regions. So the idea here is if you take the simple species that are known to be in interstellar ices and you photolize them either with direct UV photolysis or with cosmic ray induced UV photolysis, you get these radical species. I've color coded them so you can follow the chemistry. These radicals become mobile on a grain surface, which is a few monolayers of ice, mostly water ice, but with a few trace components of things like methanol and formaldehyde and ammonia. And at just 15 or 20 Kelvin, these radicals become mobile and can move around on the ice, find each other, and react. And if you just do simple combinatorial reactions between these radicals that form from this photolysis chemistry, you can build up complex organic molecules. All of these in this list are things that we commonly see in star-forming regions through observations. So this was really the first time we had a mechanism where you could directly explain the presence of many of the molecules that we see in star-forming regions. Since then, the field has really taken off looking at other mechanisms that can occur within the ice and also other types of surface reactions. And as we saw in the last talk, these three-phase physical chemical models where there's gas phase chemistry, ice surface chemistry, and then bulk ice chemistry. And all of this is really pushing forward our understanding of how these molecules might form. If you take a look at what was predicted from this first model, there are three molecules that particularly interested me. All of them are kind of chemically related to some degree because they're all modifications of methanol. There are also molecules that you can't buy in a bottle, and there are also molecules that may have some fundamental prebiotic chemical importance. And these three molecules are methoxymethanol, methane diol, and aminomethanol. The top two, methoxymethanol and methane diol, had been made in matrix isolation studies involving photolysis of precursor molecules in ozone in the matrix. Methane diol is suspected to be in solutions of methanol and water. Since I started this work, when I started at Emory, methoxymethanol has actually been characterized by the Lille spectroscopy group and has been detected in space by McGuire et al. Aminomethanol, however, and methane diol still elude spectral detection. Methane diol is the precursor to sugars in the interstellar medium. It's the simplest diol that could come off of a grain surface. And aminomethanol is the direct precursor to glycine in interstellar environments, we think. So both of these things are assumed to form on interstellar grains through this ice surface chemistry. Neither one has laboratory spectra, and neither one's been identified in space. I'm going to focus today on a set of reactions that we're doing in my lab where we're trying to get creative with how to make these molecules that you can't buy in a bottle by inserting electronically excited oxygen atoms into CH bonds in the precursors to try to make the products that we're after. These reactions have been shown to be incredibly efficient because they're highly exothermic. In matrix isolation studies, they work really well, but if you have gas phase species, there's so much energy released from this insertion that the products tend to undergo unimolecular dissociation because of all that excess energy. And so we're going to try to do this in the gas phase so that we can get rotational spectra to compare directly to observations, but we have to do it in a way where we can quench that excess energy. So I'll focus today on the formation of aminomethanol, which has really been the target of a lot of our recent work in my lab. And I'll show you some of the results that we have and some of the things that we've learned about the chemistry. So if you take a look at this reaction where you take methylamine and O-singlet D and let them react, it's highly exothermic, 152 kcal per mole. Aminomethanol is the thermodynamically favored product, but there are also other stable products that could form. The real challenge in all of this is to make O-singlet D and get it to react with methylamine. You also have a lot of other oxygen-containing species that are highly reactive in the mixture. So the way in which we do this is we take a pulsed valve and we run our gases through the valve and they pulse into the vacuum chamber. The gas expands adiabatically into the chamber and you end up actually cooling all of the gas in the expansion down to about 10 Kelvin. So that's how we quench that excess energy. What we do is we mix ozone and our precursor molecule for aminomethanol, that's methylamine, in a tube in front of this valve before the expansion, and we cross that with a UV laser. If we hit that with the right wavelength of light, it'll actually dissociate the ozone and make O-singlet D. If we do that at 248, that production is 90% efficient, but it also makes O2 singlet delta and O-triplet P as a side product. And so the O-singlet D reacts and makes hopefully the product that we're after, but we also have side reactions with the O2 singlet delta, the O-triplet P, and also the ozone that we start with. To sort all of this mess out, we actually use rotational spectroscopy, just like you would at a radio telescope, to identify the products. Here, we actually put millimeter and submillimeter light through our supersonic expansion and detect the molecules after they've formed and cooled down in the expansion. And we can scan our source anywhere from about 50 gigahertz all the way up to 1 terahertz in frequency space. This is a picture of our source in action. This light flash across the quartz capillary tube is actually the fluorescence induced by the laser hitting the tube. And you can see we've got our Teflon lenses here for rotational spectroscopy guiding the millimeter, submillimeter light through this expansion. We learned very early on in this type of chemistry that if we move where the laser beam hits that tube, we can change the chemistry that we see. If you have the laser at the top position, you have a lot of reaction time in the tube between the molecules before they go out in the supersonic expansion. If you move it down the tube, it actually changes the chemistry because there isn't so much time to react or collide and stabilize within the tube. So if you move the laser to the top of the tube, you tend to get molecules that form and are very stable, or molecules that form from multiple reactions along the way. And if you put the laser at the bottom of the tube, you tend to favor the products that form initially, whether they're stable or not. So we decided to do this experiment by moving the laser beam to 3 different positions, top, middle, and bottom, and comparing the chemistry that we were seeing when we took O-singlet D and reacted it with methylamine. Here's a comparison of comprehensive scans across this entire frequency band. We chose this particular band for 2 reasons. One, you remember back to those observational surveys from the CSO They actually started at about 210 gigahertz. So we wanted overlap with part of our observational surveys, but we wanted to start low enough in frequency that we had a lot of power in our source, and also so that we could actually compare to known lines or predicted lines at lower frequency for the molecules we were after. What we discovered when we did this was the chemistry is actually fairly similar between the top and the bottom positions, with a few exceptions. We see 9 formaldehyde lines in this particular band, and I've labeled some things here. Formaldehyde in blue, methanamine, CH2NH, there are 12 lines, it's labeled in purple. The original methylamine, the parent molecule, is labeled in orange. Hydrogen cyanide, we see 1 line. It's labeled in yellow. And then if you could zoom in on these, you can also see 20 lines of formamide as a product from these reactions. In addition to these known molecules, we see at least two unknown molecules in our products. The reason that we know there's at least 2 is we see a set of lines in the top and the bottom position that match, but we also see a new set of lines in the bottom position that don't match those other lines and don't show up in any other laser position. If we take a look at those unknowns, this is in the bottom position. The one in red actually is fairly evenly spaced, indicating a symmetric molecule of some type. We have not yet been able to identify what that molecule is. We've gone through everything in all the spectral line databases. We've calculated the moment of inertia based on the splitting. We've compared to computational databases. We've actually tried to sit down with a pencil and paper and work out based on the atoms we know we have in our system what might be forming, and we haven't yet identified it. We've also collaborated with Steve Shipman to use the AutoFit program to try to run these lines through that program and see if we could generate a set of rotational constants that we could then use for comparison with known databases or calculations, and that attempt also failed. So we're really perplexed as to what this is. If anybody has any lab data in this frequency range and has an idea of the molecule, then please let us know. We also see these other lines only in the bottom position. There are only a handful and they're pretty weak. At the moment, those don't seem to match up with any of the products that we thought should be forming from O-D plus methylamine. But there is a possibility that that could be one of those products, and we just haven't yet managed to get enough lines to be able to make a clear identification. If we take a look at the chemistry, we have other things at our disposal that we can use, other tools, to be able to try to figure out this chemistry. One of the things we started to look at recently, which has really turned into a fascinating side project on this experiment, is if we look at the time profiles of our experimental lines, we can actually see some fascinating trends. So if you look at a molecular line, so the idea here is we tune up to a given frequency and we sit at that frequency and we watch how the signal changes as a function of time. You can see here this dip in the spectrum, that's actually the RFI from our laser pulsing. So that happens over here. So that's the trigger that fires, that makes all the chemistry happen in our system. And then we see our products grow in after some delay from that signal. Formaldehyde's in the blue. It's the strongest of the lines that we looked at for this. It's got this strange double peaked behavior in time. Methanamine follows the same trend. And that first unknown, the one that was in both the top and the bottom position, also follows that trend. Formamide only has a single peak. HCN only has a single peak. And unknown 2, the one only in the bottom position, also only has a single peak. We could not figure out what was causing these double peaks. And we actually submitted the paper without having an explanation for that. And the reviewers suggested we take a look at chemical models to model the kinetics to try to understand what was going on in our system to be able to explain these time profiles. So we started collaborating with Tim Bertram's group, specifically Chris Jernigan, who is a grad student in Tim's group. Tim's an atmospheric chemist, and he had a program called FOAM, Framework for Zero-Dimensional Atmospheric Modeling. The idea here is you put in a set of kinetics information for a set of reactions, and you monitor how it evolves as a function of time. And you can either watch a parcel of gas in time, or you can sit at a fixed observing point and watch molecules flow past as a function of time. And so we ended up doing the fixed point model because that mimics the detector in our experiment. We had to assume some reaction rates because they just haven't been measured or calculated. Most importantly, the O singlet D plus methylamine reaction rate hasn't been calculated or measured, but we put all of our reactions in and we got some preliminary results that didn't give us the double peaks, but it did give us some interesting chemical information. So here's our reaction network. I know this is a lot. Let me walk you through it. So we have methylamine plus ozone without the presence of laser light. And this actually leads to ozonolysis reactions where hydrogens can be stripped off of methylamine and ozone turns into O2 and OH by undergoing that mechanism. If you add the laser light and photolyze the ozone, you get O2 singlet delta, O triplet P, and O singlet D. And then each of those goes on and reacts with methylamine to follow different chemical pathways. If you have O2 singlet delta reacting with methylamine, it can make formaldehyde and NH2OH. It can make methanamine and a whole bunch of products, or it can make formamide. If you have O triplet P, it actually abstracts hydrogens off the methylamine and ends up at CH3N. And if you have O singlet D, hopefully we're making aminomethanol. This is our target molecule over here. Aminomethanol likes to dissociate, and so immediately actually, because it's so unstable. And so it can form either formaldehyde and ammonia or methanamine and water. And if you leave O singlet D around in a mixture long enough, it will actually collide with other species and go back to the triplet P state. So we have all of this chemistry happening in our tube. And so now this model is trying to model that. I will note, if you take a look at this list of molecules, I've color-coded the ones we see in our experiment. HCN is not on this list. And so that was a big mystery for us. And then we got to reading the literature and we realized that our tube in our experiment, as I noted at the beginning, fluoresces when it interacts with the UV laser. It fluoresces somewhere in the blue. Sometimes it's a little towards the green. And we got to looking into our tube. We thought it was fused silica. It turns out to be quartz. The quartz fluoresces in the visible, and light at these wavelengths actually photolyzes formaldehyde and methanamine. And the methanamine reaction actually directly forms HCN. So if we take a look at the literature for all the information that's out there, believe it or not, the fluorescence yield and lifetime of quartz has not been measured in any way that is useful for our model. But what we have found is these reactions are very important in our chemical network. So if we take our chemical network from the model with the foam program and we add in this fluorescence and subsequent photolysis mechanism, we can actually model the results in our experiment. So we've adjusted some reaction rates here to get things to match what we see from the experiment, but nothing that we've adjusted has gone outside the realm of physical possibility. We can see the HCN grow in and decrease just like we see. So the model's on the bottom with the smooth curves and the experimental results are at the top. We get the double peak for the formaldehyde and the methanamine by taking a guess at that fluorescence lifetime. And then we see that formamide is not touched by the fluorescence at all. And so we can actually completely recreate the signals that we see from our experiment by adding that extra fluorescence and subsequent visible light photolysis into our system. And now we can make HCN. We had to assume that initial reaction rate. We don't know the branching fractions of that reaction. We had to assume a bunch of other branching fractions, and we had to assume things about the photolysis or the fluorescence for the quartz and the methanamine photolysis. However, our match is so good that now we can actually start to use the model to predict what these values should be to guide further experimental study to be able to narrow this down. The fluorescence and the subsequent photolysis was a total surprise for us, and apparently also the reviewers for this paper. But they seem to like it now because we're almost ready to go on the revision on the paper. If we take a look at aminomethanol, you will note that I have not said that we have detected it. Our model actually indicates that it should be forming at fairly high abundance, but that it reacts away. So this is the black trace here for aminomethanol. So it spikes early on, and then it reacts so quickly that it's gone before our detector wakes up. So our detector rise time is slow enough that our aminomethanol is essentially reacting out of the system before we can see it. So the next step in all of this is actually to take the model and to try to tweak the physical conditions, the laser position, and the chemistry to try to figure out how to optimize aminomethanol going forward so that we can go back and try to detect it. One really amazing aspect of all of this modeling work is we can now take a look at these time profiles for the two unknowns, and we get clues about their identity. We know unknown 1 is double peaked, and so it also undergoes photolysis at visible wavelengths. Unknown 2 does not, down here in the green. If you take a look at our reaction network, we do have a set of possible products from this chemistry that have no available rotational spectra. So we've been collaborating with John Stanton because these are all radicals and that's his expertise. So John's been helping us try to calculate structures for all of these molecules so that we can predict the spectra and try to identify what they are. We started with CH2, NH2, and so my student Connor Wright has been running a methylamine discharge experiment, trying to identify this product in a discharge and be able to nail down that rotational spectrum so that we can compare it to our laboratory results from this experiment. So in the future, we want to try to model this chemistry to better understand what's going on in that tube. We have previous results from Brian Hayes' thesis work where we did methane plus O singlet D goes to methanol, and ethylene plus O singlet D goes to vinyl alcohol. So we want to go revisit all of Brian's experimental data and try to figure out with these time-based profiles and the model what exactly is going on with the chemistry with systems that are simpler than the one that we have here. We want to use the model to optimize aminomethanol production. We want to measure the fluorescence, quantum yield, and lifetime for the quartz. And then maybe look for other tube materials that would allow us to do UV photolysis, but not give us this complicating factor from the tube fluorescence. We want to look for other products, and we need to go back now and actually center in and do some really deep integrations on a few things to try to see if we can pull some of this up out of the noise, or also move to different frequency ranges to see things like peroxide or ammonia. And then we want to extend our spectra of our unknowns into other frequency ranges for two reasons. One, to get enough lines to be able to aid in identification, but also to be able to completely overlap with our observational data so that we can go and look for those things in space. So with that, I want to thank the people that do all the work. So Katerina Yoakum, Connor Wright, Haley Bunn, and Chase Schultz have transferred to UW with me, and thank you guys for being troopers. Moving in the middle of a pandemic is not easy. Moving a lab is not easy. Doing the two things together at the same time is really not easy. Haley, by far, has led this effort on the O singlet D chemistry. I mentioned Brian Hayes. He was the first grad student on O singlet D chemistry. And Morgan McCabe came in after Brian, and so we couldn't do any of this without the groundwork that the two of them laid. And Chris Jernigan's the student from Tim Bertram's group that's been working with us. And thank you, NASA, for funding and all of my collaborators. And thank you all for coming to my talk.
Thank you, Susanna, for a fantastic talk. I really enjoyed that. I don't see any questions in the question box yet. Please go ahead and type your questions or raise your hand. I'll ask you to join in here. But maybe I can ask a question. So that step where you have a reaction between CH3NH2 and oxygen singlet D, leading to aminomethanol. Is
Yes.
that's an insertion reaction? Is that a single step direct insertion reaction without any transition states intermediates?
Yes, that is a direct insertion reaction.
Okay, so that seems then it will happen in a like a at collision rate almost, right? No, or
Yes. Yes.
okay. All right, so we do have a question. How applicable do you have? This is a question from Tom Miller. How applicable do you think this chemistry is to interstellar clouds, given that it's singlet D oxygen and the reactions involve association products?
Right. So Carr and Oberg's group has actually done some studies of this sort of chemistry in a matrix system or in an ice system where they put ozone in their ice analogs and then photolyzed, and they actually see evidence of O singlet D insertion chemistry. So I think that it is entirely plausible that this is happening, at least in the ices in the interstellar medium. It's not something I've ever tried to model in the interstellar models, but I think that certainly it is a possibility.
Okay, thank you. Is there any other questions? Okay.
Eric would like to say something. It's not actually, Susanna, we run models with O singlet D.
Oh, you did?
Yes, we are in the process of doing it, taking the reaction rates that Bergner and Oberg have done up to now about 3 carbon atoms.
That's great.
Okay,
because
thank you.
O singlet D does not last long enough in the gas and space to, right. But on the surface it does.
Well, that's fantastic.
Thank you, Professor Herbst. So I have questions, a few questions. First one from Brand Getches. In the interstellar clouds, what would you expect would be the best physical environment, high UV or cosmic ray flux?
I'm not sure that it matters because we actually see that the cosmic rays trigger a similar sort of UV radiation field to what you would see from direct UV photolysis from a star. So I'm not sure that there's that much difference between the two. That might be a better question for Eric. Ah, you didn't mean one or the other. Okay. Yeah, either one of those would work just fine for this sort of chemistry.
Okay. Okay, so the next question is from Ryan. If you assume your red unknown molecule is linear, how similar is the moment of inertia to other known species, such as like the HCN, N family, N small and capital N? So
that's a very good question, Ryan. I could probably give a whole seminar just on that. So we literally sat an undergrad down with a pencil and a piece of paper and tried to generate structures of things that we thought might be in the right frame of moment of inertia to be able to explain these lines. So far, we haven't come up with anything that hasn't been studied that is a good candidate. If you have ideas, I'd love to talk offline because we're really stumped on this.
Okay. Next question is from David Woon. You listed H2OO as a potential radical product that Stanton is studying, but H2O plus O singlet leading to H2OO oxywater closed shell. Is that a possibility, closed shell oxywater?
Absolutely. I don't think I meant to imply that Stanton was working on that one. We have him working on where's that slide? The CH2NH2, CH3NH, and the CH3N radicals.
Okay.
But yes, the oxywater is certainly a possibility.
All right. Next question is from Salma Bijawi. Did you measure the fluorescence spectra? Is there a time delay between the chemistry induced by the laser and the one induced by the fluorescence emission?
So we haven't measured the fluorescence spectra yet. We were actually in the process of doing an experiment where we had a fast camera with a photodiode detector, and we were trying to measure the time lag between the laser firing and the products, and looking at the tube fluorescence as an indicator that the laser had fired. And Haley was doing that experiment with a collaborator at Emory on the day they shut down everything for the COVID shutdown. And we haven't been able to go back and finish that experiment. So at some point in time, we will actually do those measurements. In terms of a time delay, let's take a look at this slide that I have up right now. If you take a look at the ones that are double peaked, so presumably this dip in the middle is when the fluorescence is driving the photolysis of formaldehyde and methanamine, and that is in fact delayed from that initial rise of all of the products coming in at the beginning of the chemistry induced by the laser. So there is a delay.
Okay, next question is from Maria. Thank you very much for the talk, Susanna. Do you use up all the ozone in the experiments, or is there some amount of molecular oxygen that is left after the reactions?
Right. It depends on the day. So if we have everything aligned very, very well, and if we have a nice, fresh, clean tube, we can completely photolyze the ozone. We see the ozone signal dip all the way to 0. And so we actually can get rid of all the ozone. But what happens is as we run between the ozonolysis products and the things that form from this chemistry, it actually coats the inside of the tube with this viscous black goo. We've tried to identify what the goo is, and we haven't been able to do that either. And so the laser fluence on the actual gas mixture decreases as we go. And those double peaked features disappear, and the ozone depletion starts to decrease. So we can actually change the chemistry as time evolves in our system.
Okay, this next question I really like. As a student waiting to get into this type of research, do you have any advice or recommendations into how to pursue this type of research in the future? I couldn't ask this question to a better person. Please.
Did you stage this part? Contact me. No, contact me or any of the people involved in organizing these seminars. So the biggest thing is if you're an undergraduate chemistry student, take physical chemistry. That is the most important thing that you can take to get into this type of research. If you're an astronomy student, see if you can find an astrochemistry class or dabble in a little bit of chemistry on the side so you can learn the basics. And then I think the biggest piece of advice I can give you is get involved in research and talk to people, network, and find potential graduate advisors. I know that if you contact people within the ACS subdivision, you can find a whole list of us associated with chemistry that are ready to talk with you and help you get involved in the field.
Wonderful. I'll take a couple of more questions. The last two, perhaps. Really enjoyed the talk from Joshua Halpern. Have you thought about using N2O photolysis at 193 nanometer?
Yes, we have. So N2O is an interesting case because if we used N2O to make O singlet D, then it would actually not introduce all those extra oxygen species that are giving us so much trouble chemically. The problem is that the amount of O singlet D that's produced from N2O is much less than from ozone. And we've actually tried this experiment and we see no evidence of the O singlet D driven chemistry happening in a system where we have N2O instead of ozone. So unfortunately, that doesn't seem to be a plausible route for us.
Well, the next question is from Amir. I guess it's a long question. He's asking how effective do you think the insertion reaction would be for a radical reaction in the ice mantle?
I actually don't know the answer to this question because I haven't sat down and done the math on the ice chemistry. I could talk at length about the gas phase, but not the ice. So I may have to refer you to Eric Herbst because apparently they are in the process of modeling that.
Okay. Well, the last question, how better or worse do you think your method is in comparison with the one that uses mass spectrometry?
In terms of the spectroscopic identification, I assume?
Yeah.
So the nice thing about rotational spectra is it's structure specific. And so you can actually know exactly which molecule you have, even if there are structural isomers, you can tell the difference. That being said, we're nowhere near the sensitivity of mass spec. So if you have a system where you can control the chemistry and you can use mass spec to identify exactly what's coming out, that's great. If you have a complex mixture where there are a lot of overlapping mass signals from various different species, rotational spectroscopy wins if you have the sensitivity to be able to see the products.
Wonderful. All right, so with that, I think we come to the end of this seminar. We're right on time. So thank you very much, Susanna. Thank you. Thanks to Beatrice for 2 great talks. And I really look forward to for you all to join next time, which is the 9th of December. Please join us then, and have a great rest of the day. Thank you so much.
Hi, everybody.
Thank you, Susanna. Thank you, Beatrice.